Welcome. So we're looking at the properties of rigid motions, and we should already be comfortable with the definition of rigid motions. Below, if you haven't already noticed, that there are 6 properties of rigid motions, okay? So I've gone over one which I think is a little confusing, but I want you to draw 6 diagrams for each, one for each of the properties. Okay, so I've chosen here number 3. So number 3 says rotation of a line 180 degrees about a point not on the line produces a parallel line, right? That can be a mouthful. Okay, so here I have a line, right? Notice I have 2 arrows, line, and I have a point C not on the line. Now notice that this point C is not on the line. And when I rotate my line AB, I end up with line A prime, B prime. Now these 2 lines are going to be parallel. These 2 here are parallel. They will never, ever touch. That's the idea here. So make yourself a diagram for the other 5 remaining. Okay, let's look at an example here. In the diagram below, it is given that line AB, notice it has 2 arrows on top of AB. So line AB and line CD intersect at E. All I'm doing here is describing the diagram, okay? Angle pairs that are across from each other in this diagram are known as vertical angles. So let's look at some angles that are across from each other. Notice angle CEA and angle BED, they're across from each other, so they're called vertical angles. We also have another pair of vertical angles here, which would be angle CEB and angle AED, okay? Those are also called vertical angles. And so here's our question. Although there are a few different rigid motions that would map angle BEC to angle AED, we will use the 180 degree rotation, okay, to prove this. So let's start on number 1. We're going to prove that these 2 angles are the same, that they are congruent, okay? So when ray, notice ray here, EB, only has an endpoint, one endpoint. When ray EB is rotated 180 degrees about point E, it falls on EA. Okay, so EB, when it's rotated, okay, 180 degrees, notice B maps to E, and E stays in the same place. Okay, so now EB will map onto EA. And when EC is rotated, it will map onto ED. So notice that C, when it's rotated, it too will map onto D. Okay? So now C is on D, and so EC maps onto ED. And why is this true? Well, this is true because points C, E, and D are collinear, and points A, E, and B are collinear. Remember that collinear just means that they are on the same line, okay? 2 or more points that are on the same line. And so all those 3 points are on the same line. That means when you rotate 180 degrees, it's like doing a reflection. So why then, thus, angle BEC has to be congruent to angle AED because rotations preserve angle measures, right? Just because I turn something does not mean that I change the size or shape. So let's look at parallel lines cut by a transversal. So I have 2 parallel lines. I have line here CD and line AB. And I also have a transversal which cut these two parallel lines. I have this transversal, and we call that line M up here, okay? So that's the transversal, okay? This line here is a transversal. So a few angles here to note, that we have some vertical angles here, but we also have other types of angles. And these other types of angles are called, we have corresponding angles, and these are just angles that are in the same position, okay? So if they're in the same position, they're going to be congruent. So notice here on the top, we have 4 different kinds of angles, okay? 4 angles. And on the bottom, we have also 4 angles. So you can see that angle 2 matches up with angle 6. They're in the same position. So let's call angle 2, which has a name, right? Angle 2 is congruent to angle 6. And more specifically, angle GFD is congruent to angle HEB. Notice as well that angle 1 and angle 5 are corresponding, 3 and 7, and 4 and 8 as well. So those are all the corresponding angles. We also have alternate interior angles, which are given by drawing a Z. And what do I mean by a Z? So I start on the top here, and I can go here and draw my Z. Notice that I've made 2 angles here. Here's one angle and here's another angle. Those 2 angles are going to be alternate interior. They're on the opposite side, but they're on the inside of the parallel lines, okay? So, since alternate interior angles produce congruent angles, then we have that angle CFH is congruent to angle HEB. But that isn't the only way to draw the Z. We can also draw the Z this way. If we started this side, we go here, here, and here. And now we have this angle and this angle. These are also in their interior and they're alternate. So drawing it this way gives us that angle DFH is congruent to angle AEH. So let's look at our check for understanding now. So in the diagram below, line RT and line WZ intersect at S. That's just describing the diagram. If the angles have the same measured as labeled, because there are vertical angles, so they have to measure the same, then what is the measure of angle ZST? So if those 2 angles measure exactly the same, how will you find the measure of one of those angles?